Welcome to the rigorous world of algebraic topology, an academic discipline that bridges abstract continuous geometry with strict discrete algebra. Imagine taking a flat 2D polygon and folding it. As its edges snap together, the shape transforms into a complex three-dimensional surface, like a two-hole torus. We want to know how to break these shapes apart and reassemble them while preserving their essential mathematical properties. The objective is to rigorously classify compact surfaces. We need a systematic way to guarantee that two folded shapes are either topologically identical or distinctly different. We will rely on two mathematical mechanisms to do this. The first is homology, which serves as our mathematical measuring tool to quantify the structure of these spaces. The second mechanism is cutting and pasting. This acts as our geometric construction toolkit, allowing us to physically cut surfaces open and stitch them back together into standard forms. To classify continuous geometry, we must translate it into discrete algebra. Continuous shapes are incredibly difficult to compare by eye, but algebraic equations can be systematically reduced and solved. The utility of topology lies precisely here. It takes intuitive geometric concepts and breaks them down into strict, undeniable algebraic rules. You might recall that the fundamental group, denoted as pi1, perfectly captures the topological structure of a surface by tracking how loops wrap around its holes. But using the fundamental group presents a severe computational roadblock known as the isomorphism problem for group presentations. Two completely different-looking algebraic equations can describe the exact same fundamental group. Because the variables are non-commutative, meaning order matters, simplifying these strings is taxing. There is no universal algorithm to easily verify if these complex presentations are actually isomorphic. If we cannot reliably compare the algebraic groups, we cannot reliably compare the geometric surfaces they represent. The mathematics hits a wall. We need a new algebraic tool. We must sacrifice some highly detailed structural information from the fundamental group in exchange for absolute computability. To classify surfaces effectively, we must flatten that complex, non-commutative data into a simpler, universal metric. The solution to our computational roadblock is an operation called abelianizing the fundamental group. This equation defines the first homology group, h1 of x. It equals the fundamental group divided by its commutator subgroup. The top half is the original group. Dividing by the bottom commutator subgroup forces the entire group to become abelian, or commutative. The geometric intuition here is straightforward. In this new homology space, traversing a path A and then a path B is treated exactly the same as traversing path B and then path A. Order no longer prevents computation. Let's apply this tool to an n-fold connected sum of tori, essentially a surface with n distinct holes. Looking at theorem 75.3, we can see the exact result of this calculation. The first homology group here is a free abelian group of rank 2n. We now have a highly specific, computable number. We can contrast this with the results for an m-fold connected sum of projective planes. Unlike the tori, the calculation for the projective plane yields a torsion subgroup of order 2. Theorem 75.5 formalizes what this means. Because the ranks and torsion subgroups are definitively distinct, the surfaces themselves must be distinct. Homology successfully strips away the uncomputable noise of the fundamental group to provide the exact topological invariants we sought. Homology gives us a perfect mathematical ruler to measure surfaces. Now we need a geometric scalpel to physically manipulate and standardize the shapes we measure. Moving from our measurement tools, we introduce the physical manipulation toolkit, cutting and pasting. We begin with the physical operation of cutting apart a polygonal region, denoted as P. Figure 76.1 illustrates this visually. Slicing the region along a line from vertex P0 to PK splits the original polygon into two disjoint regions, Q1 and Q2. Note the new internal edges created. To maintain topological rules, they are assigned opposite orientations. The next step is translating this precise physical cut into our labeling scheme, turning the geometry into an algebraic word. If our generic scheme is a word W1 equaling Y0, Y1, we split the word in half. We attach a new label, C inverse, to the first segment, and the opposing label, C, to the second segment. The physical act of slicing a surface perfectly maps to the insertion of inverse algebraic terms into our mathematical word. This naturally leads to the reverse question: how do we mathematically and physically stitch fragmented regions back together? Figure 76.2 reverses the previous operation. By applying a positive linear map, we paste the edge of the first region directly onto the matching edge of the second region. This creates a new quotient space entirely homeomorphic to the original unified region P. To classify any possible surface, we need a broader toolkit that moves beyond just simple cuts and pastes. This list of elementary operations allows us to reorganize the algebraic word representing any surface. Cut and paste operate as perfect inverses. Relabel and permute alter the sequence and variable names without altering the physical shape of the surface itself. Applying any combination of these moves to a word represents a completely valid topological homeomorphism. We now possess a complete, rigorous algebraic toolkit capable of transforming, simplifying, and definitively classifying any 2D surface. Let's review the core mechanisms that make this classification possible. The process rests on 4 main pillars. First, homology solves the isomorphism problem by abelianizing the fundamental group, allowing us to compute and measure holes precisely. Second, complex surfaces are built, fragmented, and simplified via the physical acts of geometric cutting and pasting. Third, we establish a system where the algebra perfectly reflects geometric structure. Every cut adds an inverse variable, and every paste joins terms, mapping visual space directly to mathematical syntax. Finally, these two tools together, the measurement of homology and the manipulation of elementary geometric operations, form the exact basis for classifying all compact surfaces. For those who want to see the complete mathematical proofs behind these operations, I highly recommend diving into the rigor of standard texts like Munkres Topology. In the fascinating world of algebraic topology,